We really see the first two day of fundamental in digital signal processing. So today we will talk about a very important issue. So remember that whenever we think about a look at a system, so a system is simply a box that takes an input as a signal and turn that into another signal, right? So the system is something a digital signal processing have to really design, right? We have some signal, let's say we have some like the example we saw in the first day of the MATLAB exercise. I have some ECG signal, which is have some noise added to it, and I need to design the systems so that the signal over here is clean, right? So you can see that we're given some input and we have to process it and provide the output. Okay, and on the first day we saw a very important class of systems. So if I can assume that this is an LTI system, if I can assume that it's an LTI system, then all I need to do is to specify the HN, the unit pole response. So HN here is unit pulse response of that systems. And any LTI systems, the input and the output simply just equal to the convolutions of the input and the unit pulse response. The unit pulse, sometimes people would call it is impulse. Okay, so just let you familiar because we would call this thing differently. So either the unit pulse response or the impulse response of the system. So the system here is really just the output when I put in the impulse. Right? So I got that. And the output, the relationship between the input and output can be completely described by the convolution. And I left as an exercise, and we can easily show that the convolution in time is become a multiplication in frequency. So you can see that the process, so that is helping us analyzing this this kind of system. So far it's very abstract. But now we have to put ourselves in the perspective of someone. Now I have to construct this system. I have to develop these systems. Someone come and ask me to design the systems. So let's say you have to design a new generation of cell phone that meet a certain standard that required by the government, right? So the signal can only go through and have to meet a certain frequency characteristic. You have to design a cell phone, a mobile phone, and you have to design a system inside it. So confront with that task, you have to design out either this edge or this. And you can see this process here, because putting this form, this thing here, we can see that it's like a filtering operation. It's like a filtering operation. A filtering in the sense that the signal here has a certain frequency. So for example, as an example here, I can have the plot of omega here, and now if I have so the signal 0 to pi, and it will come out here, and then periodic extensions. So if I have such signal, then, and if we think about designing the filter, let's say the signal here is h of omega. So when you multiply h omega with h omega, this only part of the spectrum goes through. So that's why I could filter it, right? Just really filter out the thing that you like it to go through. So that's why we're going to the topic of filter design or filtering. But I need you to keep in mind that even though this, because of it look like a filter, but it is a very general LTI system. Any linear time invariant system can be considered as a filter. Okay, so even though you go out there and there's nothing has to be filtered, you need to design some linear time invariant systems. You just simply design a filter. Okay, all right. So with that perspective in mind, let's move on here. Now I'm going to put myself now in the context of a logic designer. Let's say I design a circuit, and I have an input and output. So you think about now. So now you think like a computer, right? This is mathematical analysis. So now let's think like a computer. So you have to think in the computer, the signal x. What is the signal x? Like in the MATLAB exercise we do, we create a variable now just like a vector. So the signal x is simply having this memory location. Each of them contain a sample of the signal, right? So for example, n plus 1, n minus 1, and so on. So each of these are just a location. So the signal here, and it might have start and end, or it may just go for a while. Let's say like my speech, right? I talk to a cell phone, the signal that keeps coming. So now I have this big black box that I need to design, but what I need to get out, well, let's not draw the black box, but now let's see, how about I have an output. An output here is also a Y here, and it is also a signal, can be like that. And the job of the system, let's say I want to implement it, is having this signal, and I'm just going to fill out this slot. Right? I program a computer program to fill out this. I want to really construct a system. And let's say now, and when you compute the output, you compute one at a time. Right? You want to compute one at a time. So assuming that we are at this location, and here's n minus 1, and so on. One thing that people would typically do is, let's say I'm at this location. I am at that location. I need to know what is this value have to be. So what do I have with me now? I have my entire input, and I might have all of this sample already filled out, right? And now I simply have to compute this. Okay. So one simple way of doing that is a system called difference equation, and it's known as a DE. And the different equations is simply, when I compute this, I'm going to take this linear combinations of the input and the previous output. All the thing I have with me. And this operation can be computed very fast. So for example, I'm going to write yn equal to a1 y of n minus 1 plus a n y of n minus y of n minus capital N plus b0 x of n plus b1 x of n minus 1 s plus b m x of n minus m. Right? So this is a very simple system that I can compute. And I studied very general difference equations. And you can see that I can really easily implement them in mathematics, right? Or any circuit. So the key question we need to understand is, how should I find this number? How should I find this number? All of this number, by playing around with this number, I will have a difference equations, giving me a different systems, right? And then I can use that to, and I leave you as exercise. You can show that this is one class of LTI system. Right? So design LTI system is designing those numbers. Okay. Is it still clear? All right. So here, let me ask you a question. If I just give you this, take it as a computer, can you go ahead and implement this? Or do we miss anything else? What else do I need to specify apart from this equation? So this equation, I can run them, for n, any n, right? N is an integer, so I can just keep running that. So anything else I need to specify? I need some initial condition, right? So maybe at first start from this n location, right? I assume I have something, and then from there I can just move on. All right. So this one plus with the initial condition. Some initial conditions, note maybe equal IC, and that maybe we can give us a value of y of 0, y of m. So you can see that y of m minus 1. So having this n sample, I'm ready to go, right? I can now compute every sample. Yeah, go on. Oh, okay. So where the threshold? About here? Okay. All right. So let me put here. So this one here, what you need to have is you need to have the initial condition with required to have on the value of y and go from 0 to n minus 1. Okay. You need to have initial condition so that you can really kick off the system and it keep going. It can run. All right. So that is a simple thing. And let me say right away that all the LTI systems, all the filter that we can implement, or it's being used now, are just in those form. Okay, so this is a complete characterization of the system that's being used nowadays. Okay, or we will make the study because it's so easy to implement. Okay, so we will going to restrict ourselves to this class of systems, even though there are other systems. Because you see, if I'm going to give you, here I give you a simple example here. If I take this one here and I can write this equal to summation of h of k x of n minus k. And k go from minus infinity to plus infinity. So that's the convolution operation, right? I can show you that. I said, okay, go on, implement it. But right away you can come back and tell me, hey, but now I have this infinite sum. How can I compute it on a computer? Right? I cannot compute them in a computer. So I only can compute them with a finite number of terms. So if I only can compute with a finite number of terms, that is when I'm going to just ignore this part. Right? It's a linear combination of the input. But there's some clever class of system, it's called recursive, because if I allow those, I can allow this thing to be infinite sum, conceptually, but not actually. I'm not going to compute them, but I'm going to compute them in this form. Okay, is that clear? Let me repeat again. This convolution operation is only good for mathematical analysis. Actual implementation, you need either a finite number of terms. That means you only have this. Or, if you want to have an infinite number of terms, you cannot choose any infinite number of terms. You have to choose something satisfy this form. Okay? So that will be two classes of filters. And by the way, if you know them, I will talk more, but it is the one that has a finite number of terms is called finite impulse response. Right? You call it, this is impulse response. So maybe we say here, the filtering here, oh, I shouldn't write here. We can write up here. The two terms I would like to start. The FIR is finite. This impulse response here, impulse response, where this h of k here, then k only go from, well, h of k, well, maybe it's easy to draw now. H of k is equal to 0 outside some interval. It's only non-zero in a finite interval, finite impulse response. And this is important of that, because having that means I can compute them using this convolution. Right? Otherwise, I cannot do this convolution. And this thing comes in a little bit helping us, it allows to design some kind of infinite impulse response, but not every infinite impulse response. Okay? So that's one. Now, to understand the filter, one thing that digital signal processor use very effectively, very effectively, and we need to master that concept, is the so-called Z transform. So who here have seen the Z transform before? The Z transform. Or Z transform. Oh, there's more from Z transform. Okay, so I call them Z transform then. No, in the US we call Z transform, right? Okay, so let's practice that. So the Z transform, okay, so a lot of you are already familiar with that Z transform. It defined, let's say I have a signal Hn, Hn, and n is an integer. Then I simply computed the Z transform it by writing as Z is equal to summation of Hn, Z to minus n, and go from minus infinity to plus infinity. Okay, oh, there's one thing, yesterday someone told me, we're going to use, whenever I don't write anything, the limit here, I assume that I go from minus infinity to plus infinity. When I write the integral, I don't put the limit, I assume from minus infinity to plus infinity. It's not the indefinite integral. Okay, so that's the definition of the Z transform, and maybe we should take some example of the Z transform. Okay, so maybe I take an example here. It's just a convenient way of writing the filter. So let me take an example here. So if I have, for example, h of n equal to, okay, I'm using this notation now. So it is sequence. When I write sequence, maybe I write, let's say 1 over 2, 1 over 2. And so you think about the sequence like, so that like, you look at this guy blocking. So I write the h here is a sequence of 1 over 2, 1 over 2. and I need to know where is the origin, right? Where's the origin? So the notation sometimes I use is I just put a arrow here. So that is the origin, right? So this is where n equal to 0, and then you know that the next one is n equal to 1, and so on. And outside that is 0. Okay, so that is a convenient way of writing a finite impulse response filter, FIR filter. Okay, since I have that one, then the SZ just simply equal to 1 over 2 plus 1 over 2 Z minus 1. Okay, so that is an FIR filter in the Z domain. Alright? So that's okay. Another one, example 2 here. So now I have this filter H N, but now I make them a little bit more complicated, and I make it equal to a to the power of n, a to the power of n, maybe I put here, if n greater than or equal to 0 and 0 else. So that is a second example of another filter. So this thing here is going to be a signal, so you can see that as, let's say A is some number less than 1. So at n go to infinity, the signal will keep decaying. But this thing, you agree that it's going to go infinity, right? Maybe I can move this thing around. Okay, Z charge for all this. By the way, what I can do is I can write this signal maybe in a more compact form. Is equal to a to the power of n un. So un, where un is simply equal to this so-called unit signal equal to 1 when n bigger than or equal to 0 and 0 else. Quang, can you still see in the back? No? Okay. So this signal here, you see that I have this a to the n, and I simply multiply with this cutoff signal, which is only let the thing from n from 0 towards infinity. Okay? So I have that signal. Now let's see what is the Z charge from that signal. So example 2, continue. So to compute the Z transform, I'm now going to deal with SZ now equal to the summation when n goes from 0 to infinity, and I just plug into that signal, right? Because when n from, I have this summation from minus infinity to plus infinity. But from minus infinity to minus 1, n equal to 0. So the sum doesn't contribute. But from there forward, so from 0 to infinity, and I have a to the power of n, z minus n. Okay? Now this thing here equal to the summation, I can put them in and go from 0 to plus infinity, and a z minus 1 to the power of n. And you recognize this is just simply a geometric sum, right? This is a geometric sum. So you know that this thing here we're going to be equal to, is equal to 1 over 1 minus a z minus 1. Is that okay? There's some condition. Okay, someone already remember this. Yeah, I can only write this if and only if the thing inside here, the absolute value of this is strictly less than half, right? Otherwise the sum blow up. So this is only if the absolute value of z, so this thing here is less than 1, or the absolute value of z bigger than absolute value A. Okay, and this thing here, people call what is this? The region of conversion. So that is the region of conversion. So that is the region of conversion of the ROC. But you can see what I have here is I have a signal which is infinitely long, but in the Z transform, it have rather nice form, right? You can write Z over Z minus A. It have rather nice form, right? And you can see later on that this kind of thing actually describe some of the system like this. Okay. So who already heard about this region of conversion before? Okay, so quite a few people, and it is just simply the concept in the Z plane, right? In the Z plane, maybe I can draw them here. So here the Z plane. A Z plane is a complex plane, right? So the Z plane, and it has the real part and then imaginary part. And maybe let's say here the A sitting here somewhere, and the region of conversion of this particular filter is just anything outside. Okay. So and I led here this exercise. So for those one that haven't done Z transform before, I recommend you to try this. Now I consider another system, Hn, but now I take it equal to maybe minus a to the power of n u of minus n minus 1. I recommend you to look at these systems as a homework and to verify that this thing here also have a z. You can do exactly what I have. The z equal to exactly the same. Exactly the same. That's kind of. Except the only thing that I can distinguish between these two systems is now the ROC is when z less than a. Okay, so now that's kind of giving you two simple systems, both of them representing an infinite impulse response system, an IIR system, but having a very simple Z transform, which in turn allows us to do simple computation. So, clear so far? Okay. So now let we attack these systems. Now see, I'm going to go back and look at these difference equations. I'm going to look at this difference equation, and you understand where it comes from, right? Because of this simple way of implementing it. But now let's see if we can analyze these systems. So I assume, right, it is not hard to imagine. The Z transform is a linear transform, right? It has all the properties I will not go through. But because of that, it's a linear transform, so I can really take the Z transform of this simple equation, both sides. Right? So let me do that. So typically we take this thing here and we convert them into a Z domain. That's a very simple statement, but it representing a trick, a very, very powerful trick that an engineer, or specifically a signal processor, people doing signal processing need to master is the following. You have several domains. The transform is really mapping something from one domain to the other domain. Okay. And a lot of the time when you're dealing with something in one domain, if you find it very difficult, map them to another domain. And maybe it is simpler to analyze in the other domain. So it's really like someone with very different perspective of the world, right? And the Fourier transform we learned on the first day, the second day, you see it providing us like that. A lot of the time, think very difficult in time, you go to frequency, sometimes difficult in frequency, we go to time, right? So you really need very flexible, right? Try to look at the thing from different angle and maybe find a simple way of looking at it. Okay, so that's the key message. That's really like the trick. Typical code, allowing us to analyze, design a system very effectively. Okay, so I'm using my trick now is looking at this system, and now let's see what happened in the Z domain. So the Z domain, what is Z transform of this? YZ, right? Not too difficult. So YZ, and because the Z transform is linear, so everything can become linear, so it becomes A1. And what is Z transform of this?
Z power minus 1.
Z minus 1 YZ. It's not hard to see, isn't it? Right? Because if I take a signal and delay by n minus 1, I just replace n minus 1 here, and then suddenly there's Z minus 1 pop out. Okay? Very simple to show. And if I delay, so you see that why the Z transform is powerful, because it deals very nicely with the delay. Delay just pop out a Z minus 1. Okay? Any delay operation becomes Z minus 1. So I delay by 1, delay by n, just multiply them, so plus Z to the minus n YZ. And this guy similarly. So B0 XZ plus BM Z minus M XZ. And I can mash out this thing together, and I can write Y of Z over Y of Z simply equal to something multiplied with XZ, and that is just 1 minus summation of A K Z minus K, okay, from 1 to n, and then summation on B L 0 minus L, and L from 0 to n. Okay. So you see now the input and the output relationship of this simple difference equation can be represented now in this very simple form. And this particular guy here, just simply taking the input in the Z domain, multiply with something. And this thing, by the way, is a constant. Now this thing is something is fixed, right? It doesn't depend on the input, right? This thing doesn't depend on the input. This thing is really representing, capturing these equations. And like the convolution equations, so when I write this thing here, a very simple thing is, maybe I can put it as a theorem here. I let you to prove right away a simple, it is if x, y equal to x convolution with h, in the time domain, then simply in the Z domain, y of z equal to x of z times x of z. It's like the thing in the frequency domain, right? Everyone, well, who's seen that theorem before? Okay, one thing. If not, you can try to prove it again, at home. So by doing that, what I having here is this particular thing now is just simply a filter edging. And you can see that my simple filter like this simple filter like this here, actually implemented something realizable, because I can use the difference equation. And it allowed me to compute a filtering operation with an infinite impulse signal, right? This thing I cannot compute by the convolution operation, but I can do them using the difference equation. And this difference equation giving me this form. So is that quite clear? All right. Okay. So we have that. So now let's try to understand this transform. a little bit more. So maybe my summary statement is, okay, these two things are really directly connected. So here is, maybe I put big words here. This is for implementation. This is for implementation. I use this form, and this is for design and analysis. Right? You see, so early on we talked about we had to design a system. Design a system, or the system is given to us and we have to analyze. Right? For example, we have a biological system that we model like a linear time invariant system. So we have to analyze them. So we use the Z transform, we use the Fourier transform, and so on to design them. And then, or to analyze them. And maybe after analyze them, maybe we design a similar system. So we design something, and then when you design them, you have to restrict yourself to this form. And I can tell you that every time you have a system having this form, then you can give to a programmer to program it. Right? It is a following concept. So let me write it. Stability. You design systems, and you need to guarantee the system is stable. Stable in our single sense is called bounded input, bounded output, or BIBO, right? So the BIBO stable, and BIBO stable here saying the following thing. I have this system, linear time invariant systems, right? So now let me go to the system S, but I go to the system by H, the unit Polish form. And it have input and it have output. So as a designer, the only thing you can control is a controller system. Right? You design a system. Let's say you design a cell phone, for example. You can put all the thinking, the imagination you have in the cell phone, but then you sell it, and the user will use that any way they like. Right? So design a system, and the user will put in all sorts of different input. You'll never know. So the thing as a designer, you want to make a kind of safety. Maybe not just for the user, but for you too, is you want to guarantee that if they put, the thing you want to guarantee, if they put something okay here, nothing, well, at least something okay coming out here. Alright, so that's the thing. So, maybe more formally, this one here is BIBO if given that Fxn is less than, so if this thing here is, all of these numbers are finite, so I have everything finite, something is bounded, then the output also finite. Right? So that is a stability that we can guarantee. So that if I have an okay signal coming in here, I don't want to burn my chip, right? Or if this thing blow up, like in computer, it can give you the overfloating number, right? An overfloating number, I can have a very deadly effect. So you all know the story about one of these very expensive spaceship sent up. I think this It's number 4 from the Europe, right? From the, what is that? Area, yeah, area. So they send, inside that, so they spend about $1 billion. They send a big satellite up and then blow right away up the center. And the only single problem on that is they use an old chip, and when they do the computation, the chip, the number get overflows, right? So it just completely corrupt the system, and then it sends the spaceship something wrong, and then explodes. So $1 billion can be thrown away in a second, if the system is not stable. So that, and you never know, right? You have a cell phone, it might burn the chip, or give you something not intelligent outside. So the system is like this. The system is like that. And let's put a theorem here. I should say, not this thing here. I should say, for any input coming in that having this, we have, right? That is the stamp I can put on this system, Bibo system. Yeah. The stamp I put in is, if you put something bounded inside, I guarantee the output also bounded, right? And that for any, that's the keyword for any. So the theorem to say here is an LTI with the HN, with the HN here, HN is unipose response, is Bibo or stable, right? In the single processing, stable means Bibo stable. Okay. If and only if the summation of Hn less than infinity. Something I showed you earlier on. I give you, but now maybe we need to show that. Okay? Alright. So that is talking about these systems here. So we need to prove this. Okay. We have proved this. So maybe I'm going to do one side and let you take the other side. So if I'm going to do maybe the if part, and then to do in a homework exercise the only if part later. So if I have if summation on Hn is less than infinity, right? If this thing here is less than infinity, then for any bounded input Xn, assuming that where the absolute value of Xn, if this thing here is finite, that means I can always find a number that everything has to be loaded up. Okay, so where this thing here less than some big constant n. Okay, you agree that these other two things are the same, right? So finite, that means I can find a number where that we have, from here we have that the y output here equals the summation. Now I can use a convolution theorem. I can use convolution theorem and taking this hk, that x of n minus k Okay, running here, and I take the absolute value, I have this absolute value, the sum of the absolute is less than the absolute of the sums. Sorry. So absolute of the sum is less than or equal to the sum of the absolute, right? So this is less than or equal to the summation of hk times x of n minus k. But now each of this is a less than some number m. So that would less than or equal to some number m outside multiplied with the summation of h. Okay? And this is a finite. So this is also less than some infinite number. Okay. Is that clear, everyone? Alright. So if I have the summation is finite, then I'm guaranteed that the system is stable. Okay, so I'm guaranteed that the system is stable. And if the system is stable, then I let you ask exercise to show that this thing has to be infinite. And the trick is just constructing some signal that is finite, and also checking that this output also finite. And you got this. Okay. So the only if as an exercise. Okay. Alright, so we do see the system now, the Z domain, and see maybe the example. Remember the systems. I have a system H, and is equal to a to the power of n u of n. Right? That is systems. And we can use the Z transform, and we know that the S of Z is equal to Z over Z minus A. I did that early on, where the ROC is Z bigger than A. Okay. So this is the sequence like this. The sequence like here is n, and here we have 1, you have A, you have A squared, and so on. So here 0, 1, 2, and so on. So that is the sequence, right? The sequence having this kind of behavior. Alright? And for what A, that S would be a stable system. Is stable. It is stable if and only if the absolute value of A is less than 1, right? Because if absolute value of A less than 1, this is going to be a decreasing sequence. You can sum them up, and you can see that the absolute value is going to be finite, right? If not, you can see they're going to blow up easily, and then this sum is not finite. Okay. And if that's the case, we see that what happened on the initial, on the Z domain here, on the Z domain, remember what we had before. We had before, here is A, and here is the regional conversion, the regional conversions. Right? And the number 1 is sitting here. The number 1 is sitting there. No. The other side. The other side. Number 1 is sitting here. So number 1 is sitting there. Okay. And by the way, do we all see the fact that if I look at this circle here, this circle, the circle then, right, that unit circle, and in this case, it happened to be that the unit circle, if the system is stable, even only if the unit circle is contained in the region of conversion, right? And actually, this fact can be proved for very general system. If you want, you can try to prove that. It's not very simple, not very difficult. So let me restate the statement. A system is stable if and only if we have this. That's the first. Second, the system is stable if and only if, equivalently, the unit circle is contained in the region of conversion. Okay? So that. We're taking the Fourier transform on that, right? So remember, I have S of Z equal to summation on H of n Z minus n. So if I take H of Z, where Z is equal to Ej omega, right? What I have here is any number here, right? It is, if this angle is omega, then that would be Ej omega, right? So that means if I evaluate this thing here at this point on the unit circle, Ej omega, I plug this in here, what I have is the formula I showed you earlier on. It is a discrete time Fourier transform. So the unit circle, when I just really evaluating the Z transform on the unit circle, I obtain the discrete time Fourier transform. Okay? That's all. Okay. What I say here is a realizable implementable, an implementable system I don't know if this even have a word like that, but what I really mean is a system that can be implemented. Right? An implementable systems are an implementable LTI system. Need to have the form that S of Z is equal to a point, remember we showed before, right? It has to be a difference equation. And a different equation is something a polynomial in Z and something polynomial in Z down here. Right? So, maybe I can write here, maybe explicitly have this form. Summation of A, K, Z minus K, and summation of B, L, Z minus L, and L can go only from, let's say, L1 to L2, K go only from K1 to K2. I got everything completely upside down. It had to be 1 minus A, and it had to be B on top. Okay. But actually, we want a system that maybe need to be real-time system, not the time people design. So L here go from 1. L here go from 1, and K, sometimes people want it go from 0. Okay. So that's the form we have early on. So these systems, all we have to design is just those numbers. We have to play with those numbers. And And these systems, because it's a polynomial, right? I mean, it's polynomial in Z. The polynomial in Z, so in general I can write them equal to P of Z over Q of Z. So it is a polynomial in more general sense. I have a Z minus 1, but okay. And we do have a fundamental theorem of algebra saying us that any polynomial of certain degree would have that number. Well, let's say a polynomial of degree n would have n roots in the complex domain. Right? It's guaranteed to have n roots. So, and if this thing here is not, so I have a polynomial in Z minus 1 or Z on L1. So it guaranteed to have surely and truly that you have K2 roots here and L2 roots here. Okay. And so this one here I can always written is and if it's a root, that means there may be a constant alpha, and then the polynomial now is L from, so degree from 1 to L, I put L2 of Z minus 1 minus P1 minus 1, and I have a beta here, summation of, product of Z minus 1 minus beta, and I have a K go from 1 to K2. I hope you can see it. R1, okay, this is L, and it is K minus 1. I really need a break very soon. So I have this. So these are two polynomials. And these two polynomials here are telling me that when Z equal to one of these R, K, what happened? This thing goes to 0. This thing goes to 0. So this thing here is called the 0. The 0 of this transfer function, of this HT. Okay, this is 0. So 0, that means really where this, and I have SZ 4, I have SZ equal to 0. So that's called the 0. For Z equal to one of these PL for this, then I have S, what the SZ would be? Should have, right? I divide something by 0. So then this is one going to infinity. And that's called the pose. The pose. The pose and the zeros. So the pose is the 0 of the filter. So maybe we can go back to this filter. This filter here, this thing here, what is the 0 of this filter? 0, right? It is 0 here. And what is the pose of this filter? I, right? So I have a filter, and I can always draw. A pose and a 0. So I take a filter, and that is the Z plane here, Z plane, and it would have some pose. The pose all the way denoted by this. So everything here is the pose, and maybe it has some 0. Right? So filter, and you can see that when I specify a filter, I need to specify this. And I can similarly specify all the pose and 0 and plus a gain factor here. right? Equivalently. So a lot of the time, actually, people can specify filter by simply this plot. Where are the poles and where are the zero? Okay, this gain factor and this gain factor. Now, the poles are really the place where the thing blows up. So, the poles, can it be inside the region of conversion? No, by definition, in the region of conversion, the thing had to converge. Give you something, a finite number, converge. So that's why, for example, this filter here, the poles, suppose sitting right here, the poles here. The ROC is from that inside, right? And you see that, excuse me, the poles here is simply, this is another concept, but for this particular system where the signal, the impulse go towards infinity, so now I can run from k equal to 0 to whatever value k. And that means I just use xn minus 1 and so on. I never use anything xn plus 2 and so on. And what is the impact of that? The causal, what does causal mean? The causal means if I have run a real-time system, right? I need to predict the stock market. Right? Someone come and tell you, like, I can predict the stock market perfectly. Right? When simply I just say, but I need to predict the stock market of the price yesterday. Right? So that's the question. You need to predict the stock market. I mean, I can only use information in the past. You cannot use something in the future. Right? And that is, because it's a real time. I need to make money in real time. Now, if I do the system with a cell phone, for example, I also have to process everything in real time. I cannot, maybe I can wait, but maybe a lot of system, you need to make action right away. You cannot wait, right? So the action cannot wait, that means, so then the system is causal. Or, let's say, cannot wait. I cannot wait to get the future input to compute my system. Okay, so in that form, this is a causal system. This is a causal system. And in the causal systems, if you know about the Z transform, the ROC all the way tend to go outside. They go outside. Right? You go outside because in the summation here, you go through here and the further you go out, the smaller, sorry, the bigger the Z, and because you have a Z minus 1, you have a Z minus, Z minus 1, so you get smaller, smaller. So the message, maybe let me put the result here. So, term here is a causal LTI system is stable. A causal LTI system. So the system now is causal, right? So it goes here, and it is stable like this guy. And it's causal stable if and only if all the poles are inside the unit circle, right? So the poles is this poles here because all the poles are inside here, and those poles representing the dangerous region, the non-region of conversion, right? The region of non-conversion, and then everything outside that is okay. And if it's okay, and it's everything inside here, then it must include the unit circle. Right? You can think about this picture a little bit. So I leave this. Understand this is proof here as exercise. How about that? Okay? So let's take a short break now for 15 minutes and we come back looking at the filter design. We see that in the Z domain, right? And that can be quite powerful to understand the stability of the systems in the Z domain. So now we're going to look at the filter in a third domain, which is sometimes more important, is in the frequency domain, right? And we would move on to the technique of designing a filter. So again, the filter, I use the same letter H, but if I'm going to use omega, I assume you know that I'm talking about the discrete time Fourier transform, right? If I put the Z here, you know that it is the Z transform. So a little bit of abuse of notation here, but it's simpler to write, right? A lot of people write E, J, omega for the same, but too much for me. Okay, so we go back to this linear time invariant systems or a filter. And now look what happened in frequency domain. And that's going to give us some guidance on how to design a filter. So we got a signal X here and Y here. And we know there is a very important theorems that saying first Y of omega equal to H of omega times X of omega. Okay, and the second thing is for X n equal to E J omega naught n. So some sequence like this. Then moving through H, we get Y of n equal to H of omega H of omega naught times E J omega naught n. Okay. So these are the two theorems we proved the first day. Maybe we should spend some time to understand this part a little bit. So what this really mean? Because this is a complex exponential signal, so maybe hard to recognize them at first. So now I'm going to see. So now consider another one here. So 1, first 2, and now 3. Now let's say I'm going to look at the signal xn equal to something we're more familiar with, namely the signal of cos of omega naught n plus, maybe just like that one. Right? So this is a very simple cosine signal. Right? This is simple cosine signal. And it can be written as, I can use Euler formula, so I can write this thing here is equal to 1 over 2 E J omega naught n plus E minus J omega naught n. So I consider this signal, which is not hard to imagine, right? It's oscillating signal with a certain frequency, omega naught. Okay, so I fix omega naught, I have that signal. And it can be written in this. And now I'm going to put this signal through the system H. Then I would get our Yn is going to be equal to this 2. So it's 1 over 2. And I'm going to have here H of omega naught E J omega naught. Are we okay with this? Okay. Ej omega naught plus h of minus omega naught Ej omega naught n. Okay. So that's what we get out here. So we have that signal then, and one thing we know. So let we assume. So now assume that h n. So the thing I'm trying to do here is this is a complex signal. The filter is complex, and this may be a complex signal. But now I want to look something more realistic, something that the signal maybe when we collect is a real signal. So this is a real signal. And I assume that the filter is also real. So then the output is also the real signal. And I want to see what that real output look like. Alright, so that's what I'm trying to do. So assume that Hn, this thing here, is real. Is a real filter. That means each of these numbers are real. Then it's not hard to show that the h of minus omega is simply equal to the h of omega, but you take the complex conjugate. Alright? Everyone alright with this complex conjugate notation? Okay? Now you've seen this notation before. So what we have here and is a complex conjugate number. As a number here plus a complex conjugate. Right? Because this is complex conjugate and this is a complex conjugate of that. Okay? So what happens when you have two complex numbers that is complex conjugate each other, you add them and divide by 2. You got a real number. And what the real number would be?
It's a real one.
The magnitude that multiply with the Ej of the phase of that h omega. Right? Any number, and maybe you can see here. So if I have the z here, then it's always equal to r times Ej of theta. Right? Where this is a theta here. Right? So that is the complex number. And what we have here is our number z. So I add z with its complex conjugate. This is the z complex conjugate. Right? The complex conjugate is exactly the one that here is the real axis and here the imaginary axis. Okay. When you add these two numbers together, you got these two vectors, and you divide by 2. So what you get out is this real part. What you get out here is the real part of this complex number. Right? Z plus z minus 2, so z plus z complex conjugate over 2 equal to the real part of z. And what is the real part of z? If I take this, so this is equal to r cos of theta plus jr sine of theta. So the real part of it is simply equal to r times cos of theta. Right? So that's a simple. So now, when you take this, so this number is equal to that, multiply Ej this, and now this Ej join this thing here, go to exponential, and when I take this trick there, I got this. Okay, so I don't see that. Alright. So this thing giving you something quite important to remember. Very important. If I take a signal that is sinusoidal, so maybe you can draw here. So the sinusoidal signal, but remember our signal is a discrete. So maybe we have a sample, some random location sample here. Right? So I have this input here. I put it through the system S, the system H, I mean. Then what I get out here is another sinusoid cosine signal where the sample are now. And two things happen. The sinusoidal signal, and this is one particular frequency, omega naught, right? This cosine signal goes through H, two things happen. One, the amplitude of this thing here get magnified by H omega naught, which is the absolute value of this. Second, this thing here gets shifted by this, right? So a filter, when I design having this, a complex number, have a magnitude and phase, they do two different things of the signal to the output. The magnitude magnify and the phase delay. Okay, so that when you look at the filter, you can see what each component does. Alright, so that concept clear. Now, typically, what we do want to have, what we do want to have now here is understand the impact of this, because a signal can be decomposed into this component or this sinusoidal. So a typical filter, you want to do something like, okay, I want to pass a certain frequency. I want, for example, all the omega naught within certain range get through. That means I want to make those numbers big or small. That's where I need to. But associated with that, I have this shift. I got this shift. And that shift, this signal here, you can see this shifted here. This shifted here. When you want to write them, maybe I get to write y of n is equal to h of omega naught and then time cos. So I want to put up a cos function. So it can always write the cos function of omega naught, and then inside here I got n plus the phase of h of omega naught over omega naught. Okay, right? And now if this thing here equal to a constant, I assume I have this thing equal to a constant, let's say constant alpha here, for example. So if the magnitude of h omega naught is equal to alpha omega naught, then what happened? The phase shift is constant for every frequency. Doesn't matter what omega naught is, it always shifted by the same amount. Right? Now what happens if that's not the case? If that is not the case, then for different frequency, it got shifted differently. And that would be very deadly, because let's say I play music here, like boom, 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 so different frequency play different time. I pass through a filter, right? Design a really good filter. I go over here, different boom, boom, boom in different frequency. Now they got all mixed up, right? And then you got very distorted music. Can you see that, right? Because we learned yesterday the content in the speech or the voice signal is time and frequency. Right? I say certain words at certain time. Now I got a filter. You design a filter for a cell phone system. The person down and hear exactly the same frequency, but now mix up. So it could say word by word and so on. Right? So is that clear? So the message here is, if you have a filter, you wish to have a linear phase filter. So this one called the linear phase, right? The phase is linear. So the message here is, it is important to have linear phase filter. Okay, so this is LP. All right, and that's really the thing here. So you say here, this is amplified frequency component, amplified frequency, and this is the part that would delay a frequency. I would say a frequency component in the signal. Right? A signal, any signal can be decomposed in different frequency components, and that for that particular input, the output get amplified and get delayed by these two. Okay. And that's why we need to have a linear phase. So the question, how can we design a system with linear phase? Right? That's what I would like to have. So maybe look at some examples and see what do we have. Okay. Example now and study. So take an example now. So I'm going to study a simple filter H n, which is 1/2, 1/2. And this is the origin. If I tell you to implement this system, can you describe the input? What does it do? I filter a signal with that filter. Just take the sample xn plus xn minus 1 and divide by 2. Right? Just taking the average. Right? Taking the average. And let's see what this filter is doing to our signal. And I want you to take the average, right? And intuitively, early on we see that doing this average, you can do more, but I just put 2 here. Seem to have an effect of smoothing out the signal. But now we want to see really why. Okay, so to do that, then, well, we need to go to the Fourier domain, because filtering becomes multiplication or having something like that. So the edge of omega is equal to, by plugging the formula, 1/2 plus 1/2 e j omega. Okay? And we need to find out this, so it is just these two things. Maybe I pull out E. The trick when we get to this, I want to find out something like, I want to represent it in this form, something of a real number multiplied with EJ to a complex, some real number. Right? I want to represent them in this phase and magnitude. Okay. So that is what we thank you. So that's what we're trying to do. You see, I can give you something like this alone. It still doesn't tell you much about the system, right? Because you see, we need to know the phase and the magnitude. Okay, maybe I should put here some words here. So this is, the name here is the magnitude. And this thing here is the phase. A filter, when we talk about the filter, we're not just talking about this, we talk about the magnitude and the phase. of that filter, because it's important that as I described. Okay, this and the trick to do is I want to make them in that form. Then I have this thing here. So this is 2 pair of complex number, and you know that when you add, remember if you have, so put it here, recode that if I have 1 over 2 ej theta plus e minus j theta, what that give me? Cos of theta. Cos of theta. Okay. So that is so I want to really play around with this so that I have something that I can get the real number out. Okay. So that's my play. And to do that, then you see the trick now is you want to factorize so that this thing is right in the center. So minus j of omega over 2, right? And I have here these other 2 parts, so that give me cos of omega over 2.
Yes.
No, it's divided by 2. Okay. Alright? So everyone happy with this? So that giving me that. So now we have to plot out the phase and the magnitude. So, and we're going to do this. Oops. So this is going to be the magnitude, and this is the phase of h omega. And here is omega. And as we learned before, all we have to do is just go from minus pi to pi. Because everything else is going to be repeated. Minus pi to pi. So having that function there, the first thing I need to do is maybe going to plot out this cos of omega over 2. So cos of omega over 2, at omega equal to 0, what does it? It's a 1, right? It is equal to 1. And then at omega equal to, and then you're going to go down. And then when omega equal to 2, so equal to pi, so you're going to touch 0. So it goes something like this. Okay, something like this. So that actually is always not just a real number, but it's always positive. Right? Because remember this thing here, it not just have to be a real, but a positive number. Right? So I have this. So in that case, then that's simply the magnitude. And what is the phase? The phase is minus omega over 2. Right? So minus omega over 2, that means it would be having this line. When equal to 0, equal to pi would be pi over 2. So it would be something, the line like this. This is a line of minus omega over 2. Alright? So that is a filter. This filter here, that's the magnitude, that's the phase. This is a linear phase. It is linear phase, right? Because straight line, linear lines. So this is a good filter. It's a good filter in the sense that it can everything go through and it lays them the constant speed. Right? So I don't have a mess up problem. Now what is this filter is doing? Well, you see the signal when omega equal to 0, it can't go through. And then slowly decays. So at omega equal to pi, it rejected. Right? So let's see what the signal between these two, right? So when omega, so look at this signal, cos of omega n, this cos of omega n, right? This basic signal. Well, when omega equal to 0, what I have is just cos of 0, 0, 0, 0, 0, so it's just constant signal. Boom, 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 right? That. When omega equal to pi, what that signal would be? Boom, 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 right? Such as 1 minus 1, 1 minus 1, 1 minus 1. So something oscillates extremely fast. That is a high frequency. Where this thing here oscillates, well, it's a constant, very smooth signal. So what it's saying here is the signal coming in, the component is a smooth, get go through, where this kind of component get what out, get Q out, get filtered out. Right? Is that clear now? So this filter, now we see in the frequency domain, we see something. What we would expect before is that it actually smooths out the signal because it preserves the low frequency and filter out the high frequency. Okay? So that's the message. Okay. Now that is a simple case. So now maybe I don't want to show the filter, but let's say I assume now, how about I assume that instead, okay, maybe I do another one here. That is an important concept. Omega equal to the magnitude is times the E of J and then the phase of H omega. Okay. And this is real and bigger than 0. Right? Bigger than that or equal to 0. You agree, right? This thing is real and bigger than or equal to 0. Now suppose, you see in this case I got this, many filter, actually I can tell you ahead, if the filter is symmetric, so if you have something here and this end here has something the same, something here and then something here the same, you can really group them together, right? And it's something pop out and something, a real number coming out here. Right? So suppose more general I have H of omega equal to A of omega times EJ of theta omega. I have this. And what I can have here is a real, and this thing here is a real. Oh, this obviously is real, right? But you see, I really cannot guarantee that, this I'm lucky. I'm lucky that this thing here is a positive, a real and greater than or equal to 0. But there's a case where this thing can dip. This part can go down to non-zero. So negative. Then this thing here, if that was the case, then I can write this thing here is also can be equal to, in the case of negative, the equation here is I can write that as minus of A of omega. I do the minus, so I multiply this thing by minus 1. I multiply this by minus 1, then I have to multiply it by minus 1. Right? This is after that they give me the equation. Multiply it by minus 1, I put them in here is, okay, is EJ of theta omega plus pi. You agree that these two things are the same? Okay. So if that's the case, then now if you want to equalize this with that, then I can write now that the absolute value of omega now would be equal to A of omega if A omega is bigger than or equal to 0, and equal to minus A omega if A of omega less than 0. Okay, so that's the part. And in pan, the phase of H of omega will be equal to, well, in that case, then I can use this form, because real and positive. So that must be the phase. Right? That's the fact, right? Any complex number is uniquely represent a real non-negative number multiplied with this exponential. Right? Because that's just a polar coordinate system. In that case, this phase equal to theta of omega if A omega greater than or equal to 0, but this thing here is minus, no, this is phi omega plus pi else, if maybe else. Alright, so that's pretty clear now. Alright, so we have that, and maybe, alright, so we, in general, if we have that, that's the filter we have. Now, I'm going back to the case where the filter is symmetric. Symmetric, you know, I can always group like this. And I have something out here. So one thing for sure is something here is linear. This is a linear phase. But if this thing here is still negative, I cannot guarantee that it have a linear phase, but this has something else. Okay. Maybe a short example. And then I can talk. So, for example, if I have an edge of omega equal to A omega times Ej theta omega. So maybe let's plot it out here. Let me just draw the thing from 0 to pi. 0 to pi. Okay. And for example, the A here, because A, let's say the A coming something like this. Something like this. So that's the A. So there is the A of omega. Okay. And here is the theta of omega. That's the theta omega. So now when I have to convert this thing now to the complex, to find out the magnitude and the phase of that, then the magnitude of this would be this function, and then I take the absolute value of it would be this. So this would be the edge of omega magnitude, right? In the range of this thing here, positive, I just have to take that, but it's negative, I have to take the negative part. Now, for that the case, and the phase of this, so let's call this thing here is a pi over 2. So the pi over 2 here, this thing here, what happened? I have this thing here going down here, and then all of a sudden, it jumped up here. You're going to end by pi. And then it goes down here. So that would be the phase of H omega. Okay? So what people would call here is this is a pi jump on the phase. This is a pi jump. And where do we have that jump? Where do we have that jump? Where this thing goes across 0. So only jump when H omega equal to 0. The magnitude of this equal to 0. Right? Is that clear? Alright, so this jump, but this jump actually is daily jump because I thought I originally have a linear phase like this. Everything delayed, you know, by the amount set. But all of a sudden, it did the thing, then it destroyed the linear phase like we have. You agree, right? So this is not a linear phase filter. It's not a linear phase filter. But in that case, and this filter, the filter having that form, where, let me repeat, this is real, and this part here is real. The only difference is real, but still can be negative. Where this thing here is real and non-negative. Right? The only two different. But the filter having that general form where if I have a theta of omega equal to some alpha times omega, if I have this, is called generalized linear phase. Okay, GLP. Okay, so you see the GLP is the generalized version, but it's as good as a linear phase. Right? It's as good as a linear phase for the practical purpose. And in the homework exercise, we're going to generalize that because you can imagine now if any symmetric filter, you can put in that form by just grouping the terms, symmetric terms. Right? You get something real out and you can put that. Okay, is that concept clear, everybody? We now want to look into how could we design a filter that meets a certain requirement. Right? So that is the topic, the last topic of today's lecture, is the filter design. Filter design. So that is the filter design topic here. Let's take a simple case. Take a simple case here. Someone come and tell you, okay, I have this signal coming in, and in the discrete domain, and I really want, so from 0 to pi here, I want all the signal from from minus omega naught to omega naught to go through. And anything else, I want it to filter to reject it. Right? So that is an ideal filter. So suppose that someone asks you to design a filter like this. So filter, they read the requirement, right? So you can imagine the requirement. Let's say you play music and you want to turn the knob and you only want to get that really low beat, like boom, 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 where all these things get rejected. Okay, so you want to design that filter. And the question I have also in mind is, I want to design a filter that I can instruct someone to design a circuit or a computer program to run it for me, right? So that's the message. So this is, let's say, it is an ideal filter. So the SD omega is the desired filter. The filter that I really want, right? The filter I really want. So I say, okay, if I have that filter, not a big problem. Let me take the inverse DFT, inverse DTFT, and see what that coefficient look like. And then I tell you to do the convolution, right? So that's the first part. So you take that, and now you want to do the inverse. So you have this Hn of the desired filter. What that would be? A sinc function, right? Anyone remember what that sinc would look like? Sine of maybe omega naught n over omega naught n. Maybe. I'm not sure, but okay, let's assume that. There may be some term here. I don't need to check it, right? But like my story, my message I want to have. What happened with that filter? What is the problem with that filter? It's gone forever, right? Because the same function, as you know, is going to wiggle, even though it's going to die, but it's going forever, and you have a sample here. So you cannot tell someone to take that filter to compute, right? Because you know that if you have to compute this, I have to compute yn equal to summation in x in hk x of n minus k and I have a k go from minus infinity to plus infinity. We say, okay, take that, put in that formula, compute it, no problem. Oh, no. Computer cannot do that. Right? So you have to do something. So what should we do? Cut off, right? Cut off. Okay, so maybe this thing is small, right? So throw them away. Right? So you can do that. You can cut off something and throw them away, but then you have to go back and say, okay, what happened when I cut them off? So the shape now will be changed, right? So to cut them off, so now let's say, and to cut them off, what do we do? I think about that, I have the whole world in front of me, right? I say that, you know, I can only work if I can see everything, but now I only can have the window. I only have to see a finite line. So I can only see the thing through that window. So the thing we do here now is we multiply them with a window. You tell me you cut off and maybe make it more general. So now I get a filter now, h of n here is equal to a Wn times is design, the ideal one, where this thing here have a finite length. Right? So I take a finite line, I multiply this, so now I got a finite line. So this thing here will be finite line as well. Then I can work with that one. So here's where the thing that we saw yesterday come in place, because multiplication in time is a convolution in frequency. So h of omega now equal to h of the design one, and I'm going to convolve with this w, and then get omega. This convolution is the convolution of from minus pi to 2 pi. From minus pi to pi, the formula I have. So, we go back to the exactly same problem early on, right? This is where the trade-off comes in, because you say, okay, I really want that my h look as close to this guy as possible, right? Because I want to get it as close. And the only way I can make it as close as possible is to make this thing as small, narrow as possible. But if you want to make this very narrow, that means you make this thing wider, right? And of course, make this longer and longer, that means you have to run this thing slower, right? For example, so that's where the thing comes in, right? So people ask you to design a cell phone, and they say that the maximum I can allow you is about 30 sample delay, because otherwise, you know, the microprocessor couldn't compute fast enough to run in the real time. So you construct like this, only have 30 numbers. 30 numbers with this. That means for every sample output, I have to make 30 multiplication. Right? You see that the length of h is the number of multiplications per sample. So the longer you have, you know, the longer you have to wait. Either computationally wide, or you have to make this thing wait for a while before you can have the next output. So you see now, I'm going to put myself as an engineer, which is fine. I can do anything you like, but you have to, you know, spend the cost. So now as an engineer, we say, well, now this is constraint we have. I only can have a 30. What is the best 30 numbers I should use? Alright, so that, and the best 30 number is what is the best window I should use of 30 lines. So you see that. And I do tell you yesterday there is a very simple way to do that by simply, as you said, cut off, right? Cut off is this cut off here. That means I just truncate them. So maybe we can draw them out here. You may just have to take my word for it, because I don't have a MATLAB here, but in the afternoon you would run the MATLAB and verify all of this by yourself. Very simple, we have all the tools. So now, here's omega, and we're going to draw 0 to pi, because you know that everything will to repeat. And 0 to pi is when you have thing turn, one side, and from 0 to minus pi, everything turn the other side. Right? So the frequency I will see, 0 is the lowest frequency, pi is the highest frequency. Right? So the ideal filter is this one. This ideal filter. That's ideal filter. Of course, it requires infinite light. So if I want to have simply cut off them, then what do we have is something like, we will have something like this. And then I'm going to draw maybe I'm going to draw the magnitude, right? Because it's a real. So this is the edge omega absolute value using the rectangular window. Rectangular window, so that is a rectangular window. I take a rectangular window, simply kill off everything outside. I got something like that. And remember this rectangular window, this thing is quite narrow, but it has a lot of wiggle. So the wiggle going to create this thing, wiggle here. Right? So now you're going to use another one, which is the Hamming window. Is I take this window here, slowly go and here. So that is a Hamming window. Well, the Hamming window, we're going to make this thing broaden, so you got something much nicer here. But now you're going to broaden out. Right, so that's what's going to happen. And this broaden out here is due to the fact that this thing here is really no broaden out. Right? Maybe I should draw a figure on here. So omega. So the idea that would be the idea W, right? The one that's really concentrate all the energy in the origin. So when you convert, you got exactly the same amount. The Hamming, the rectangular window, what color you use? Yellow. So it has something like this. You're going to be going down here, but you're going to wiggle. So that is the W of the rectangular window. Okay, so that's why you see those wiggle here, when you convert the two things. The Hamming is going to be, you have to place something that you get broader down here, but then you're going to be much smaller down here. So this is the W of the Hamming. Okay, and you see that effect. We saw early on the effect on doing the spectral analysis, but it also similarly happened on the frequency filter design. Right? You got lenses, and this thing here, what people call is a ripple. Ripple, and this thing here, people call transition band. Transition band. Because here's okay, here I let thing go through. Here I going to kill thing. But in here, that's where it can have a transition band. And the Hamming simply make the transition band wider. Okay? But so one more thing, one more filter design, and then we would take a break. Let's say I tell you something. Okay, maybe so the ideal filter in the continuous domain. So here the continuous domain. Someone tell you that I want to have this filter here, and now in the frequency domain F here, and now the H continuous domain here, H of continuous domain design filter of F is cut off at this F naught. How can I map from this F naught to the omega naught? pi f naught over t. Exactly. All is equal to 2 pi over t is really the sampling frequency. So equal to f naught over sampling frequency. Right? Is that clear? Yes. And now assuming that I'm going to design a line N filter and it is a causal filter. So it's causal filter, that means N would go from 0 to N minus 1, right? The filter has a sample going to positive direction. So the question is, I really have to find out this number, right? Finding out this number, I can plug into this formula and I can run the systems. So find this number is very, very difficult. Well, that is the problem of filter design. And we have one technique before, which is select an ideal filter and we window them, right? With some correct shift and delay. Now another technique now is, say, in certain applications, you know that you want to have an ideal filter. So maybe going back to the ideal filter, that is ideal filter to pi here. So that is ideal filter. H of omega ideal. And you can easily see the problems that we cannot have is we only have n degree of freedom. N degree of freedom to play. And we want to get this, so this n degree freedom giving us some filter h omega. And this h omega is the function that have value for every value of omega. So we cannot twist all of these numbers so that this thing matches what? Exactly every omega. Right? So that's the thing. So if I have n degree of freedom here, what is the maximum I can hold for? What is the maximum I can match? N, right? So I can have n, then maybe now I can specify. In this here, I want to have h of omega equal to h of the design filter omega for omega equal to some omega k. K go from 0 to n minus 1. That's the best I can hope for. Right? So now, for example, I want this very critical location. This location here, I want the filter to have to match. I want the filter to have to match. Right? So that I want the filter, my ideal filter go through those. And what I hope for is, okay, so the actual filter, it would go through this point. So these are the points that it crossed. It match the ideal filter. But in between, I have no other guarantee. I just hope that, okay, because if this thing is a finite line, so you can easily show that this thing here is a continuous function. So we're going to very, very continuously here. So if it is, okay here, maybe nearby is not too bad. That is the idea. Okay. So if I have that, then what? Okay. So maybe the question was early on. The number of degree of freedom, maybe you can write them down explicitly now. So we erase from the beginning here. So in the technique with so-called frequency sampling, right? Frequency sampling, you can see that I sample the frequency of the ideal filter. I sample this thing, but only at those certain moments in frequency. I enforce it equal to I enforce this filter I'm going to design equal to this ideal filter. Right? What do we have? We have h of omega, and we know that that is our desired filter, our real filter. And in summation, it n go from 0 to n minus 1. It is H and E J omega n. So now enforce constraint that I have H of omega k equal to this H design of omega k. Right? So they are the sequence of number. And here is I have to enforce. Right? For k go from 0 to, maybe I like to make it more general here, to k minus 1. Enforcing that would leave you something like this. I will have a summation of h of n e j omega k of n. Here n go from 0 to n minus 1 and equal to this h d of omega k. Alright? Now in this case here, let me circle. These are the unknown. Right? These are one that I want to find. These are one that I want to really get. But everything else is known, right? Because I know this thing, I know this value. So then, what is this? It's just really a linear system, right? And then you can solve. So this is amount to this is just simply a system of linear equation. Right? So this, you can see that this is system of linear equation. How many unknowns? N unknowns. How many equations? K equations, right? N unknown K equation. Right? Because I have this thing here for K, from 0 to K minus 1, and these are unknown. Right? So that's what I say early on. You can hope for at best enforcing about N. You can have more, but then you have to solve a least square solution. You can have a less, you may have to equal something else. Right? It is a thing that you have to solve a linear system equation. Okay? What do you predict? What happened? What kind of case is that? We have something like Fourier transform, right? Remember, taking the discrete Fourier transform is simply sample the DTFT at those equal space locations. Right? So the edge, this edge here, the edge of omega k, the edge of omega k is simply equal to the edge of k, and this thing here is the DFT of Hn, taking the DFT of like n, right?
That is the next
Of what?
that is omega k. No.
And now instead of enforcing only a certain point, I want to enforce anywhere, but now with some tolerance. I allow them to wiggle, but I want to control that wiggle. So the thing here, for example, I have this filter, and I would say that, okay, here's my ideal filter, but now I'm saying, actually, I really want from 0 to SP. I really want the signal go through. From omega s to pi, I want it going to be stopped. So this is, from here to here, is so-called the stop band. Right? This thing here, I really want it to go, it's going to be rejected, right? This part here is the pass band. And there's this famous thing that you already see it come down, okay? This thing here is the transition band. So now a more powerful technique, I want to specify this. And I want to specify so that I really want that in the stop band, the signal going to wiggle, but wiggle with some tolerance of delta S. Right? Actually, I want it to be 1, but I can allow it go to be 1 plus delta S or 1 minus delta S. Okay. In the transition band, because there's like no man land, I don't care. I let go whatever I like. And in this band here, I want it to be, kind of above certain level. So that is delta P. No, I got everything upside down. It is delta P, and it is delta S. Okay. So that is the kind of more accurate requirement, right? Because remember here, with only n degree of freedom, I cannot hope to achieve perfect everywhere. I can only either achieve perfect for a certain set of points, or I want to achieve the best I can, but with some tolerance. Okay, so that's it. And this actually the most powerful technique. And it's done by the filter design technique, is known by Park, McLaren design technique. Very well-known technique. Park actually was a master student at that time. He was just doing masters. And actually, 2 years ago, Park and McLaren, they won a major award in DSP because it's used routinely in signal processing. Okay, so what is behind that technique? They set up the problem like this, and then they know that the filters they can design are going to wiggle inside here. They're going to wiggle. They're going to wiggle inside here. And the filter, because I cannot enforce them, it's going to be a continuous function, but I'm going to be I'm going to control it so in this range and this range. So you wiggle inside here. And you're going to get the best one, right? You try to get the function. So this thing here is the function h omega that can be written as summation of some h and ej omega n. And n go from 0 to n minus 1. So this curve here is, even though it's a function from 0 to pi, but it's controlled by only n degree of freedom. So and here you see that actually is a polynomial. And because it's a polynomial and we're going here, and you really force them, so actually in the optimal case, you're going to hit all of these boundaries. So that's called, this filter going to be the solution. The solution, and that part we can really prove, is an equiripple filter. It's not hard to see, right? Because I really want to enforce something that is kind of above certain here. So when it hits, it's going to, the ripple, they all will be the same, right? Because if anything less, I can really push it more, right? Because I really push them to the limit. So you can easily show that. And if it's an equal ripple filter, actually we know that you're going to hit this point, and they give you a set of equations which you can solve. So that's the thing behind the technique. And there is so-called, actually this in the optimization, this is because of the alternating theorem. If you learn about optimization, you probably learn about this theorem, right? This is a Chebyshev optimization problem for polynomial. Okay, so I won't have time to go through that, but just give you the motivation, the concept, and we don't need to know the detail because this is just a command in MATLAB. So this command in MATLAB is a command called remix. MATLAB here. MATLAB is a remix command. You know that is a really the algorithm to do this optimization, if you know about that. So in the afternoon, you would experiment with this and look at the filter and see the major.